I'm reviewing 4.5 practice, forces with vectors. And the first example, the first question, giving you this grid saying each box is 10 by 10. And we're asked to draw these three vectors, so 20 newtons south. Letter A looks something like this. Of course, you can draw these anywhere on the grid. Question B, 45 newtons south. Again, each box is 10. This is 10, 20, 30, 40, and then 45. We go halfway through the next box. So that's 45 newtons south. That's C. 15 newtons east. Again, you can draw this anywhere on the page. There's 10, and then halfway, 5, 15. 15 newtons. Newtons are the units of force. And to the east. Okay? Compass rose is always on the right to help confirm the directions. Question 2, the difference between the two vectors that they give you, a force that is 5 newtons west and a force that is 25 newtons north. So what's the difference? Depending on where you draw. I think the first difference you may write is the magnitude. So we could say each force has a different magnitude. Either the word magnitude means mass. Each force has a different magnitude and in a different direction. So remember that forces are vectors, which means that they have both magnitude and direction. So each force has a different magnitude and direction. And then if we were to draw that, 5 newtons to the west would be using the same compass rose up here as west being to the left. And then 25 newtons to the north would be approximately 5 times as long. So yesterday we went over this example of Karina and Lavelle kind of playing or fighting over this toy. And so maybe the first thing that they would be doing is maybe playing tug of war with it. You had one person going this way, that's Karina. Okay, for Karina. And she would apply 25 newtons to the east. And then we say, well, Lavelle, 5, 10, 15, 20 newtons to the west. And they're kind of playing tug of war with it. So that's one option to happen. And there's various options to come up with. Another one we could say would be Karina pushes down on the truck. So 5, 10, 15, 20, 25. That's Karina. So she applies a force of 25 newtons to the south. And then maybe Lavelle pulls 5, 10, 15, 20 newtons to the north. And I'm just putting this kind of on the front of the truck so that we can count the boxes and make sure our intervals are scales kept consistent. Using L for Lavelle, doing that. Alright, so we've got them pulling it left to right, we've got them pulling it up and down, and then maybe they actually agree with each other and help each other. Maybe it's a heavy toy, and so Karina, 5, 10, 15, 20, 25, helps lift the truck up, so applies an upward force. I'm going to try to stay consistent with what I did earlier. I'm not going to use that arrow. What I should do is start here and go with it. 5, 10, 15, 20, 25. So that would be Karina again, helping to lift the truck. Maybe it's a heavy toy. and Lavelle as well, 5, 10, 15, 20. They both apply a force to the north. Okay. And just for the sake of maybe net force factor, since these arrows are both pointing in the same direction, the net force on the truck would be 45 newtons to the north. We add those. In this example, since they're applying a force in opposite directions, you'd subtract them. So the net force would be 5 newtons. And since this is the larger force, it's going to be 5 newtons to the south. Same thing over here, you'd subtract them, and the net force would be 5 newtons to the east. Okay, taking a look at the back, question 4. If you want everybody to interpret the forces on the truck from this last question, the same way, what important pieces of information should you specify? And I think the most important thing to specify is the scale. If we're going to interpret each of those drawings, similarly, the scale needs to be kept consistent, and our scale was that 1 box equals 5 newtons of force. Alright, let's calculate the net force. Those arrows are pointing the same direction, so that those two forces can be added together. So there's a net force on this pot of 22 newtons to the east. Alright, this will accelerate since it has a net force on it. Okay, the basketball has 12 newtons to the west and 8 newtons to the east. Since those arrows point opposite directions, you subtract them, which leaves you with a net force of 4 newtons. Okay, this arrow is larger, this force is greater, so the ball will move to the left. So the net force is 4 newtons to the left, or 4 newtons to the west, however you want to say that is fine. And here's a hanging plant. Okay, again, these arrows point opposite directions, so we subtract them. 5 newtons minus 5 newtons equals 0 newtons. Okay, now this is a hanging plant, so typically these just hang in place motionless. So if you have a net force of 0, the object is either motionless or has a constant velocity. Now for a hanging plant to have a constant velocity, I suppose somebody would have to be lifting it up off the ground to the place where it's going to be hung, and so it would have a constant velocity in the vertical direction as you're lifting it up. You could have it moving with constant velocity. Alright, and then finally, I think we've just answered this question. If all the forces acting on an object are balanced, then the object is what? So I should probably clarify then. Out of these 3 examples, so this one will accelerate, and the forces are unbalanced. Okay, how do I know it's unbalanced? Well, there is a net force, 22 newtons to the east. This one over here will also accelerate for the same reason, because the forces are unbalanced. Okay, now this one's motionless, or it has a constant velocity. Okay, and we're going to kind of star this one. These forces are balanced. Okay, so this is the only example where the forces are balanced. Okay. So now we know that when forces are balanced, 2 things could be true. Either it's not moving, which sometimes we term motionless, or it's moving with a constant velocity. So it could be A or B. Okay, both of those would be true.